Last time on Mastering AMC 1012, we looked at expected value and the very powerful tool linearity of expectation and use it to crack two problems. Today, we're exploring another useful technique, recursion. So what is recursion? Recursion is a process of solving the problems for small cases and then writing a recurrence equation to calculate it for larger values. So essentially, there's three steps to a recursion problem. There's the base cases. You find the values for small n, generally 0, 1, 2, 3, it depends on the problem, but generally small values. And then you write a recursion equation. And for this, you have to look at cases. You look at the different cases for the nth of something based on the previous values. And then you iteratively calculate higher values. And then you get your answer, just like that. Also, a meta-solving tip, sometimes in these kind of recursive problems, you can do engineering induction, which basically means you look for a pattern and you assume that it's true. It doesn't always work, but it's a helpful tool. Keep in hand, you can check out in my meta-solving video. Okay, let's see this in an example, because it will probably make more sense then. Recursion. How many sequences of zeros and ones of length 19 are there that begin with the 0, end in the 0, and contain no two consecutive zeros? But they also can contain no three consecutive ones. It seems like a lot's going on, and there's definitely no way you're case break matching this one because there's just too long. 19 is too much. Let's explore the general structure. You begin with a 0, you end with a 0. So there's no two consecutive zeros. So there has to be 1 next, right? But there's also no 3 consecutive ones. So from here, we can have another 1 maybe, but then it has to be a 0 because no 3 consecutive ones. Or we can have a 1 and then directly become a 0. From here, then what? It just starts all over again. Next one has to be a 1 because no 2 consecutive zeros. Then we can have another 1 if we want, or we can just directly become a 0. It seems like a cycle here. Maybe we'll end somewhere. We'll end at a 0, just like that. Okay, so how do we do this with recursion? Well, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1. It seems like we have these repeating subunits over and over again. And we end at the 0. Let's tackle this for small cases. What if it's length 1? Not 19, just 1. Seems like a boring question, just 2, 0 or 1. We don't deal with any. Or, wait, actually, no, it can only be 0 because our condition says it will begin with the 0 and end with the 0. So just one way, actually. Has to be 0. Now, what about 2? Has to end with the 0, begin with the 0. But uh-oh, no 2 consecutive zeros. So this isn't allowed either. 0. Okay, now what about for 3? For 3, it has to begin with a 0, end with a 0. And there has to be 1 in between. And this does work, so there's only one way in this case. Okay, I think we have enough base cases for now. Maybe we'll come back and get more if we need them. This is for 1, this is for 2, this is for 3. Okay. Let's try to find a recursive equation now. Remember, that's the second step. Recursive equation. How do we find that recursive equation? Well, what if it's, let's try to relate a sequence of length n to a lower sequence. So it ends at a 0, it starts at a 0. And remember, we have these 0, 1, 1, 0, 1 units that always must be true until the last 0. So we can think of, maybe instead of trying to add values to the end, because that's not possible anyway, it's a 0, let's add values to the front. This won't always be true. Most times in recursion problems, you'll be adding to the end, but in this case, it's better to add to the beginning. So for something to be of length n, there's really two possibilities here. Again, we're breaking down into cases, different cases like I mentioned. The two cases for the start of a value of length n is 0, 1 or 0, 1, 1. And then obviously followed by a 0 and then some other digits. So can we express this in terms of lower values? Well, length of n, 2 in the beginning, then there's n minus 2. Oh, wait, that looks like there's 0, 1 in the beginning. It looks like this is n minus 2. So let's write a function. Just to make our observations more clear, we'll write a function f of n. F of n is the number of such sequences for length n. It's equal to, if we have a 0, 1 at the front, then it's f of n minus 2. Basically, if the first two digits are 0 and 1, then now the number of ways to do the remaining digits, that's just f of n minus 2. Why? Well, begins with a 0, ends with a 0, and it can be whatever else in between. That's n minus 2 total digits. Okay, now what about the first three digits? 0, 1, 1. Well, those also have one way again. And there's n minus 3 digits remaining. And they begin with a 0, end with a 0, n minus 3 total digits. So if it starts with 0, 1, 1, then there's just f of n minus 3 ways. Okay, so now we have our base cases. Let's just say f of 1 is 1, f of 2, 0, f of 3, 1. Let's try to find f of 4. So f of 4 will be f of 2 plus f of 1, which is equal to 1. F of 5 is f of 3 plus f of 2, right? 5 minus 2 is 3, 5 minus 3 is 2. Is also just 1. Seems like a lot of 1s here. F of 6, well, f of 6, that's just f of 4 plus f of 3. F of 4 plus f of 3 equals 2. Oh, our first above one value. Okay. Now let's just keep going. Maybe let's go a little faster now. So f of 7 will just be f of 5 plus f of 4, which is 1 plus 1 equals 2. Let's go here now. F of 8 equals f of 8 minus 2 plus f of 8 minus 3 equal to 2 plus 1 equals 3. Oops. Okay. f of 9 equals f of 7 plus f of 6, which is 2 plus 2, 4. F of 10 equal to f of 8 plus f of 7, 3 plus 2 equal to 5. We have to go to 19, so we still have a while to go. F of 11 equals f of 9 plus f of 8, which is just 4 plus 3, 7. F of 12 is f of 10 plus f of 9 equals 9. F of 13 equal to f of 11 plus f of 10 equals 12. F of 14 equals f of 12 plus f of 11 equals 16. F of 15, f of 13 plus f of 12, 21. F16, f14 plus f13 equals 28. F17 equal to f15 plus f14 equals 37. F18 equals f16 plus f15, 49. Finally, f19, f of 17 plus f of 16 equal to 65. And that's the answer. Okay. Next off, we have a problem from Amy. Before, let's just quickly recap this problem. Basically, what we did is we found the base cases first, then we wrote a recursive equation using the cases, and then we just iteratively calculated all the values till 19. I know this seems a little bit tedious at the end, but it would have been a lot worse if we had just done casework. The recursion saved us, and now we're moving on to another problem. Okay, in this problem, a collection of 8 cubes consists of one block, one cube, with edge length k, for each integer k. A tower is to be built using all 8 cubes according to the rules. Any cube may be the bottom cube in the tower. Any cube may be the bottom cube in the tower. And it looks like that's repeated twice. Let's just ignore that. The cube immediately on top of a cube with edge length k must have edge length at most k plus 2. So what does that mean? That means on top of something k, it can be at most k plus 2. So it can be k plus 2, k plus 1, k minus 1, k minus 2, so on, all the way to 1. But anything can be at the bottom. Let t be the number of different towers that can be constructed. And we're just asked for the remainder. So let's just find t. Let's find t. But 8, that's a big number for this problem because there's going to be a lot of cases to cover. Let's recurse. F of 1. F of 1. So f of 1 is just 1 cube. Just 1. Now, what if there's 2 cubes? If there's 2 cubes, then we can have either one on top of each other. Because anything can be at the bottom, and let's say that's 2, for example. If the 2 cube is at the bottom, then 1 cube could be on top. Because 1 is has to be less than k plus 2. So if this is k, this has to be at most k plus 2. And in this case, that is definitely held true, because 1 is much less than 4. And the other way around also works, because 2 is less than 1 plus 2, or 3. So f of 2 is just 2. Now what about f of 3? F of 3 is where it starts to get a little bit tricky. So from here, let's try to find the recursive equation. Okay, what is the recursive equation in this case? How can we find it? So the trick to finding the recursive equation in this case is to see what cases are possible for the cubes. Let's say we already have k minus 1 cubes stacked in whatever order, we don't even know. But we assume that they does work. Okay, so now to get to f of k, we have to add another cube. Where can we add it? Well, any cube can be at the bottom. So, does k at the bottom work? It will work as long as this cube is less than k plus 2. But we don't have to worry about that, because this is already the first k1 through k minus 1 cubes. And k minus 1, the highest possible number, is definitely less than k plus 2. Okay, so k at the bottom, that gives us one case, right? What other cases? Oh, wait. We can just put it on top of a cube where the edge length of that cube, what can be the edge length of a cube if it goes on top of? Well, if we put a cube on top here, it says that the cube immediately on top of a cube with edge length k must have edge length at most k plus 2. So this cube plus 2 must be, this cube over here can be at most 2 more than the number of this cube over here. So k can be at most 2 more than the number of the cube of below it, right here. At most 2 more, which means it can still be k minus 2 and k minus 1. Anything lower? Too big. K minus 2, k minus 1. So that's 2 more choices. Is there anything else? Well, we've considered the case where it's on top of nothing, and we've considered the case where it's on top of anything. That's it. 3 choices. Well, 3 times the number of ways to stack k minus 1 blocks, that is. So now we have a different recursion from the one we've seen. F of k equal to 3 times f of k minus 1. Isn't that interesting? How it's just 3 times more as you add each more, because you have 3 choices. Oh, but you might notice, this is times 2, not times 3. This recursion must be wrong. Well, it turns out this is a special exception. The reason being, well, there is no k minus 1 cube to place on top of. So the 2 cube cannot be placed on k minus 2, cannot be placed on cube 0. There's no cube 0. Because in this case, k minus 2, where k is 2, would be 0, and there's no 0 cube. That's why it's times 2 and not times 3. But for anything larger, we should be fine, because you can place at the bottom. Cube 3 can be placed at the bottom over cube 3 minus 1, and over cube 3 minus 2. Over cubes 2 and 1. So there's 3 choices. So from here now, f of 3, 2 times 3 by this recursion, f of 4, 2 times 3 squared, so on, all the way till f of 8. So f of 8, well, we multiply by 3 every time from f of 2. So we multiply by 3 6 times. 2 times 3 to the 6 equals 2 times 729 equals 1458. But we want to find the remainder when divided by 1,000, so 458. That's the answer. Next up, we have to call a set of integers Spacey if it contains no more than 1 out of any 3 consecutive integers. How many subsets from 1 to 12, including the empty set, are Spacey? Now you're starting to get the hang of this. So we know what to do first. Base cases. 1. How many subsets of 1 are Spacey? Well, there's really only 2 subsets. 1 and the empty set. They both work because they both only have one Spacey thing. They only have one number that's even part of it, so we don't really have to worry about anything there. Okay, next. 2. 1 and 2. Does all 4 cases work? Well, it turns out we can have one number just fine. We can have the empty set. But we can't have both of them. Because then more than 1 out of any 3 consecutive integers is contained. It contains 2. They're both consecutive. So there's 2 consecutive integers. So that doesn't work. But there's a total of 2 squared by the subset formula. 4 subsets. 1 doesn't work. The other ones all do work. Because 1 element is just fine. It says no more than 1, but 1 is 1. So 2 squared minus 1, 3. Okay, and this is f of 1. This is f of 2. And let's just find one more. F of 3. F of 3 for f of 3, we can again have the empty set. We can then have any one element subset plus 3. And that's about it, unfortunately. That's it. Having 2 elements, there's 3 consecutive integers. So having more than 1 integer in this whole subset will result in more than 1 out of 3 consecutive integers. In this case, 1, 2, 3. So 4 choices. Okay, we're now ready for the step 2, the recursion. What is the recursion in this case? Let's see. 1, 2, till n. Okay. So, what is our recursion going to be like? Well, let's take, what are the cases we should take? Well, there's 2 cases really. N is part of the subset, or n is not part of the subset. So, the first case, n part of subset. N is going to be part of the subset. The second case, n not part of the subset. Okay, how many ways if n is not part of the subset? Let's start with case 2 first. Well, if n is not part of the subset, then anything from 1 to n minus 1 will work. To explain why that's true, look here and see that if n is not part of the subset, then from the values from 1 to n minus 1, anything is allowed. Because the only condition is that no more than 1 out of any 3 consecutive integers can be contained. And in this case, the consecutive integers are n minus 2, n minus 1, and n. But if n is not contained, then it's not putting any restriction on n minus 2 and n minus 1. Because those are the only 3 consecutive integers it's part of. So if n is gone, then they can be whatever they like, as long as they satisfy the conditions for n minus 1. So in this case, it's just f of n minus 1 ways. Interesting. But what if n is part of the subset? If n is part of the subset, then it's going to be a little bit more complicated. So our condition says that no more than 1 out of any 3 consecutive integers. These are 3 consecutive integers right here. So no more than 1 So if n is the 1, then n minus 2 and n minus 1 are not the 1. That's going to be out of those 3 consecutive integers. But n minus 3 can be, again, because it's not part of those same 3 consecutive integers. In fact, anything n minus 3 and left does work. And the reason being is that even if n minus 3 or something lower, like n minus 4, even if something like n minus 3 or n minus 4 would be to include as part of 3 consecutive integers, none of them are part of 3 consecutive integers near n. Okay, so that means it's just going to be f of n minus 3. So recursion is just f of n equals f of n minus 1 plus f of n minus 3. So to recap, what we did is we looked at the 2 cases, n is part of the subset and not part of the subset. If it's not, 1 through n minus 1 can be whatever they'd like. If it is, n minus 2 and n minus 1 can't, but anything left not part of the 3 consecutive integers can, f of n minus 3. Now we just iteratively keep going until we get till 12. So f of 4 is equal to f of 3 plus f of 1 equals 6. F of 5 equals f of 4 plus f of 2 equal to 9. F of 6 equal to f of 5 plus f of 3 equal to 13. F of 7 equal to f of 6 plus f of 4 equal to 19. F of 8 equals, I'm not going to write the whole thing now, just f of 7 plus f of 5, which is 19 plus 9, 28. F of 9 equal to f of 8 plus f of 6. F of 8 is 28, f of 6 is 13, 41. F of 10 equals f of 9 plus f of 7, 60. Right? Just 40 plus 20. And finally, f of 11 equals f of 10 plus f of 8, 88. And now, finally, f of 12 equals f of 11 plus f of 9, 88 plus 41, 129. And that is the final answer. 129. Okay, so basically, we found the recursion, we found the base cases, and then we plugged it in to get our answer. The standard pattern for a recursion problem. But sometimes we have to use recursion for probabilities, and this is what we call states. Now, states is very powerful, but you're going to have to check it out in the next video over here.